Exercise 3.13 is called More on Quasi-Linear Utility. And the utility function that is given in the exercise is the one that is depicted here on top of the screen. And it shows you the utility that a person derives from consuming two goods, X and Y, and they appear additively in this utility function. And then there are a couple of questions, and the first of these questions is show that this function is not strictly concave and explain your result. Now, for concavity, a couple of things need to hold. First, we need that with respect to both goods, the first derivative is positive. So the derivative of this utility function with respect to x should be positive, which holds in this case because it is given that the derivative of the function f, which we don't know what it is, but we know that the first derivative of this function is positive. So that is okay. But the second derivative of the utility function with respect to x needs to be negative for the function to be concave, strictly concave. So that implies that the second derivative of this function f needs to be negative, and this holds as well. Third condition is that also with respect to good y, the first derivative needs to be positive. Now, the first derivative with respect to y is the derivative of y with respect to y is equal to 1, which is positive, so that holds as well. But then finally, also the second derivative with respect to y needs to be negative. Strictly concave, it needs to be strictly negative. And we have that the derivative of 1 with respect to y is equal to 0, which is not strictly negative. So we conclude that this utility function is not strictly concave. And that completes exercise A. Then we move to B, and B asks you to show that the function is quasi-concave. So, and the phrase quasi is key here, and explain again this result. Now, for quasi-concavity, it needs to hold that for the function, the following needs to hold. The second derivative with respect to x times the square of the first derivative with respect to y minus 2 times the cross-partial derivative with respect to x and y times the first derivative with respect to x and the derivative with respect to y plus the second derivative with respect to y times the squared of the first derivative with respect to x. All this needs to be negative if you sum the three parts. Now we know already from A that the second derivative with respect to y is equal to 0, so the third part does not appear here. And we know that also the cross partial is equal to 0. Because if we take the derivative with respect to y, that one is equal to 1. But then if we take the derivative of what with respect to x, because the x does not appear anywhere in the 1, that derivative is equal to 0. So of this complicated expression, the first and the second term, they do not appear. They are both equal to 0. So it needs to be the case that the first term is negative in order for this entire thing to be negative. Now, does that hold? It does hold because we know that the derivative of the utility function with respect to y is equal to 1. We square it, and the derivative, the second derivative with respect to x is equal to f double prime x, and we know that this thing is negative, so we also know that the entire thing is negative, and this condition holds. So we conclude we have shown that this utility function is quasi-concave, and that completes question B. Then for C, we specify this quasi-linear utility function, and we take the specification that is given over here. So y is plus 1/2 the natural logarithm of 1 plus x. And then we need to show explicitly that the indifference curves for this case are vertically parallel. And what is the marginal rate of substitution when x is equal to 1? And y is the function a natural logarithm 1 plus x rather than a times the natural logarithm of x. And notice here that an a is added in the exercise, although in the utility function that is given, there's no a appearing anywhere here. So we can forget about that a little bit. But the marginal rate of substitution is identical to the derivative with respect to x divided by the derivative with respect to y. Now the derivative with respect to x is 1/2 and then 1 over the derivative of what's in parentheses within the natural logarithm. So the derivative of this thing with respect to x. No, I say that wrong. So let me do that correctly. So if you take the derivative of this part with respect to x, so d ln 1 plus x with respect to x, then in the numerator you get the derivative of the thing within parentheses with respect to x, which is equal to 1, and in the denominator you get the original expression within parentheses, which is 1 plus x. So if we plug that in here as well, we have 1 divided by 1 plus x, and the derivative of u with respect to y is equal to 1. So if we do this together, then we get 1 over 2 times 1 plus x. Now then if we fill in the value x equal to 1, then for that particular value the marginal rate of substitution is equal to 1 over 2 times 1 plus 1 is equal to 1 over 4. Okay, so and then the question is, show explicitly that the indifference curves in this case are vertically parallel. Now they are vertically parallel because the marginal rate of substitution is only a function of x, meaning that for any value of x you get, if you go vertically, each indifference curve with that value of x has the same slope, because the slope of the indifference curve is identical to the negative of the marginal rate of substitution. And then we're done with C. Then for D we have a different specification of the quasi-linear utility function, where we replace fx with 2 times x to the power 0.5, which of course is equal to 2 times the square root of x. Now again we can compute the marginal rate of substitution. We know that the derivative with respect to x is equal to 1 over the square root of x. The derivative with respect to y is equal to 1, just like before. So the marginal rate of substitution is these two things divided by each other, and we have 1 over the square root of x divided by 1, which is 1 over the square root of x. Now, if again we take the value x is equal to 1, and we find that for that value the marginal rate of substitution is equal to 1. Now what we can do is that we take this second utility function and we just try to depict a couple of indifference curves. And what I will do, so I will make a graph. So something like this. And we want to take the indifference curves associated with a utility level of 10. Now, for this utility function, we know that if utility needs to be equal to 10, for example, what we can do is we can take a value of y equal to 0. So if we take over here in this utility function y equal to 0, what then needs to be the value of x such that we end up with a utility of 10? Well, it's the value for which 2 times the square root of x is equal to 10. So we need a value of x that is equal to 25. So we know that 25 units of x and 0 units of y give this individual a utility of 10. Now, can we find the second point on the indifference curve? For example, take a value y equal to 2. What is then the number of units of x that this individual needs in order to get a total utility of 10? Now, in that case, 2 plus 2 times the square root of x needs to be identical to 10, meaning that 2, the square root of x needs to be equal to 8. So the square root of x is equal to 4 and x is equal to 16. Now we can plot this in our graph. So a value of 25 and for x and 0 of y gives us a utility of 10. But also if we have 16 units of x and 2 units of y, we also get a utility of 10. And if we connect the dots, then we get our indifference curve. And also note that if we don't consume any units of x, so if this thing over here is equal to 0, then we need 10 units of y in order to get a utility of 10. So our indifference curve intersects with the y-axis at the value of 10. So this is equal to 2, and about here we have a value y equal to 10. Now we can draw the indifference curve, and it runs something like this. And what you see is that it cuts right through the x-axis. So in question C, the question is, are the indifference curves for the function in part C and D asymptotic to the x-axis, such that the marginal rate of substitution comes really flat once we approach the x-axis? Well, you can see from this indifference curve it does not. And from just looking at the marginal rate of substitution, you might think, oh, but if we take x larger and larger, if we let it go to infinity, then the marginal rate of substitution will go to 0. So just from considering the marginal rate of substitution, you might think that these utility functions, the indifference curves, are asymptotic to the x-axis. But they are not, because we cannot get x, let it go all the way to infinity, because for that to happen, our indifference curve needs to be in this area over here where y is negative. And we cannot consume negative units of y. So already here we bump into the y-axis or the x-axis, which is long before x becomes infinite. So to answer C, the answer is no. The indifference curves, they are not asymptotic for the to the y-axis, and it depends on the value of y, because y cannot get negative. So that cannot hold in the first utility function, but also not in the second. Yeah, and that is about all that there is to say. There are no differences between the utility function in C and the utility function in D. And I think that completes the entire exercise over here.